Hello, I'm Joseph Kasser, and welcome to this podcast where the AI team does a deep dive into some application of systems thinking.
All right, so get ready. We're going deep into the story behind Liz CJ1,
Liz.
the world's very first commercial solar power plant.
Oh, wow.
Just imagine this. It was built way back in the mid-1980s
Yeah.
with technology that almost seems, well, prehistoric compared to what we have today.
I can imagine.
I mean, they had limited resources, tight deadlines, a multinational team with, all sorts of communication barriers.
Yeah.
And get this,
What's that?
no formal requirements documents.
Really?
Like none.
Wow.
And yet they still managed to pull it off.
That's impressive.
Liz CJ1, it became a spectacular success.
Yeah.
So our mission today is to kind of unpack how they did this, and we're focusing specifically on the control and electronics system,
Some brains of the operation.
Exactly.
Yeah.
And we've got some excerpts from academic papers about Liz CJ1 that really get into the nitty-gritty of the CES.
Cool.
So, are you ready to uncover the secrets of this pioneering project?
Absolutely. Let's do it. What's remarkable is how relevant the stuff they did like over 40 years ago still is today to systems engineering.
Yeah.
These principles, they're surprisingly relevant even today, whether you're designing complex software, managing a team, or even just like solving a tricky problem in your everyday life.
I'm already so intrigued.
Yeah.
So paint a picture for us.
Okay.
Well, what did this solar plant actually look like?
Okay, picture this. A vast expanse of the Mojave Desert.
Okay.
Scorching sun, shimmering heat waves,
I can see it.
Yeah. Now imagine hundreds of these massive parabolic mirrors, each one shaped like a giant satellite dish.
Wow.
Spread across an area like the size of a football field.
Huge.
These mirrors were strategically positioned, to concentrate sunlight onto a pipe. And this pipe was filled with oil. And that oil was heated to incredibly high temperatures.
Okay, so we've got concentrated sunlight heating up oil. What happens next?
Right, so that superheated oil was then used to generate steam, which in turn drove a turbine, just like in a conventional power plant.
Okay.
And that turbine, spun a generator, producing clean electricity.
Mm-hmm.
It was a symphony of engineering brilliance, harnessing the power of the sun to illuminate homes and businesses.
It sounds pretty straightforward in theory, but I bet there were some serious technical challenges involved,
Oh, for sure.
especially back in the 1980s.
Absolutely. The real magic and the real challenge, it was controlling those hundreds of mirrors.
Right.
Each mirror, it had to track the sun's movement across the sky
Yeah.
with incredible precision.
Wow.
We're talking like plus or minus 0.2 degrees of accuracy.
That's tiny.
To put that in perspective, it's like hitting a bullseye from miles away every single day.
Oh, wow. That's some serious accuracy.
Yeah.
I can already imagine the headaches they must have faced.
And remember, they were doing all of this with 1980s technology.
Yeah.
No fancy GPS systems, no sophisticated computer modeling. It was all about ingenuity and resourcefulness.
So let's dive into the heart of the operation,
Okay.
the Control and Electronics System, or, CES.
Right.
I understand this system was actually conceived in Jerusalem, far from the, scorching Mojave Desert where the plant was built.
That's right. The control system was designed and prototyped in Jerusalem and then shipped to California for installation.
Oh.
Talk about logistical challenges. And it wasn't just about transporting the hardware. It was about making sure that system would function perfectly in a totally different environment.
I can only imagine the communication hurdles they must have faced.
Oh, yeah.
And we haven't even talked about the technical constraints.
Right.
Didn't you mention limited testing space in Jerusalem
Yeah.
and an unknown electromagnetic environment in the Mojave Desert?
You're spot on. They had to deal with all sorts of unknowns, potential interface issues. They had components coming from different countries.
Yeah.
You got the harsh desert conditions and the ever-present pressure of tight deadlines and budgets.
It sounds very stressful.
It was a high-stakes game, very little room for error.
It almost sounds like a recipe for disaster.
Yeah.
To make matters worse, you mentioned that their initial prototype design was completely unsuitable for large-scale deployment.
Yeah.
What were the main issues with the prototype?
Well, for starters, they were initially looking at a mini computer-based central station, which would have been incredibly expensive and complex for the time.
Yeah.
They were also considering Ethernet links, which were pretty cutting edge back then. But, that carried a higher risk because the technology was still relatively new.
Makes sense.
And the local controllers in their prototype, they were essentially Dumb.
On dumb local controllers.
Yeah.
It sounds like they were setting themselves up for a logistical nightmare.
It does, doesn't it? They were essentially trying to control hundreds of mirrors from a single central point with very little intelligence distributed throughout the system. Plus, they had these issues with the three-phase motor controllers, constantly blowing their silicon-controlled rectifiers. The prototype was a far cry from a robust, reliable system that could operate smoothly in the unforgiving desert environment.
So how did they turn things around? What was the key to their success?
This is where things get really interesting.
Okay.
So knowing they had this unique project with tight deadlines and even tighter budgets, they knew they needed to rethink things, like radical rethink. What they did have was a team with a wealth of experience and a knack for asking the right questions.
Okay, that makes sense.
Yeah.
Instead of blindly following the initial plan, they took a step back and assessed the situation. What were some of the critical questions they asked?
They started by challenging the very foundation of their approach. So instead of getting bogged down in technical details, they asked these really fundamental questions like, what are the essential functions this system must perform to generate electricity? What's the most efficient way to control and monitor hundreds of mirrors spread across a vast area? How do we deal with unpredictable events like intermittent clouds or sudden gusts of wind?
Yeah.
It was all about understanding the core purpose of the system and identifying the critical challenges before diving into solutions.
So they were trying to define the problem clearly before jumping into solutions.
Right.
That seems like a pretty fundamental principle.
Yeah.
But I bet it's easy to overlook when you're dealing with, complex engineering challenges.
Oh, yeah.
Did they manage to distill these questions into some kind of high-level requirements?
They did.
Even without formal documentation?
And this is where their commitment to simplicity really shines. They boiled down the entire project to just 2 high-level system requirements.
Yeah.
So, the first one was a no-brainer. The system had to generate more power than it consumed.
Makes perfect sense. What was the second requirement?
The second requirement was equally straightforward. Maximize power generation each day.
Okay.
They recognized that every bit of sunlight captured, translated into more clean electricity, so efficiency was paramount.
Right.
These 2 simple requirements, they became the guiding principles for every decision they made from that point forward.
So they had their North Star, their 2 guiding principles.
Yeah.
But how did they actually break down this complex challenge into manageable chunks? It's one thing to say maximize power generation.
Yeah.
But it's another thing to actually design a system that can do that reliably day in and day out.
You're absolutely right. That's where functional and physical decomposition came into play.
Okay.
So they started by breaking down the system's functionality into these basic actions. Think about what a single mirror needs to do. It needs to stow itself in a safe position when not in use.
Right.
Deploy itself at the start of each day.
Okay.
Track the sun's movement across the sky. Allow for manual adjustments if needed.
Yeah.
And of course, idle when there's no sunlight to capture.
Okay, so they broke down the mirror's tasks into manageable steps. What did they do next?
Then they mapped these functions onto a physical architecture.
Okay.
They envisioned a central station,
Right.
like the brain of the operation, responsible for overall control and monitoring.
Right.
This central station, which they called the CS, would communicate with over 600 local controllers, or LOCs, each one controlling a single mirror in the field.
So it was like a hierarchical structure.
That was the initial thought.
Like the central station issuing commands and the local controllers carrying them out.
But here's where they made a brilliant decision that would significantly impact the entire project's success.
Okay, what's that?
They decided to adopt a distributed, self-regulating approach.
Wait, so instead of the central station micromanaging every single mirror,
Yeah.
they gave the local controllers a degree of autonomy.
Exactly.
That seems pretty forward-thinking,
It was.
especially for the 1980s.
It was a game changer. By shifting intelligence and decision-making power to the local controllers, they dramatically reduced the workload and the complexity of the central station. Remember, they were dealing with limited computing power.
Yeah.
So this distributed approach was like a stroke of genius.
I bet it simplified a lot of things.
It did.
Instead of a rigid top-down control structure, they were moving towards a more flexible and adaptable system.
Exactly.
This brings us to another key decision they faced.
Okay.
How to actually control the movement of those mirrors.
Right.
Didn't you mention they had two very different options?
They did. And this choice really highlights their commitment to simplicity and their willingness to challenge conventional wisdom. So when it came to mirror positioning, they could go with a complex equation-based approach, requiring precise knowledge of all sorts of parameters: the mirror's exact location, the sun's position in the sky, and even factors like wind speed and temperature.
Okay.
Or they could opt for what they called a sloppy algorithm.
A sloppy algorithm.
Yeah.
It doesn't exactly sound like the recipe for hitting that 0.2-degree accuracy target. I'm dying to know which path they chose.
It might sound, I don't know, counterintuitive,
Yeah.
but their sloppy approach was actually a stroke of brilliance.
Okay.
And it all goes back to, those tight budget and time constraints.
Right.
A complex, equation-based system
Yeah.
would require way more powerful and expensive computing hardware, not to mention the added development time.
Makes sense. So they were being pragmatic,
Yeah.
choosing a solution that fit, their constraints.
Exactly.
But how could a sloppy algorithm possibly achieve the accuracy they needed to maximize energy capture?
That's the beauty of it. The sloppy algorithm wasn't about being careless or anything. It was about leveraging the inherent properties of the system to simplify control. Think of it like a thermostat in your home.
Okay.
You set a desired temperature,
Yeah.
and the thermostat just switches the heating or cooling on or off, to maintain that temperature. It doesn't need to know the exact temperature at every moment.
Right.
It just responds to deviations from the set point.
I see. So the sloppy algorithm was more about creating a self-correcting system,
Right.
rather than trying to calculate every movement with, absolute precision.
Exactly.
Did this approach actually work?
It worked beautifully, and it came with a whole bunch of advantages.
Like what?
Well, first, it meant they could use simpler, less expensive hardware,
Okay.
both for the central station and the local controllers.
That's a big win, especially with their limited budget. Any other benefits?
Yeah, the simpler software also meant lower data rates between the central station and the LOCs,
Okay.
so they didn't need to transmit huge amounts of data back and forth,
Right.
which simplified the communication system and reduced the risk of errors.
So it was more efficient in terms of both hardware and communication.
Exactly.
I'm starting to see why they called it a stroke of genius. Can you walk us through how this sloppy algorithm actually worked in practice?
Sure, imagine a single mirror.
Right.
Its local controller, it's receiving instructions from the central station
Yeah.
about the sun's general position in the sky.
Right.
Instead of trying to calculate the exact angle to point the mirror,
Right.
the LOC would simply aim it a little bit lower than the target.
Okay, so it starts with an intentional kind of undershoot.
Right.
What happens next?
Then the LOC would activate the mirror's sun sensor and
Okay.
start slowly rotating the mirror upwards, searching for the sun.
Mhm.
As soon as the sun sensor detected sunlight, the LOC would stop the rotation. It had found its target.
So it's like the mirror was actively searching for the sun
Exactly.
rather than being precisely guided to its location.
And once it locked onto the sun, the LOC would continue tracking its movement,
Okay.
but with a slight overshoot each time.
Mm.
It would move the mirror past the sun's position, wait for the sun to catch up,
Okay.
and then repeat the process, constantly correcting for any deviations.
It sounds like a simple yet incredibly effective way to maintain accurate tracking
It would,
without,
yeah.
complex calculations.
Hmm.
Did they come up with this approach entirely on their own, or did they draw inspiration from, other fields?
Interestingly, this pattern matching technique was actually inspired by satellite control systems.
Mhm.
They realized that the challenge of tracking a satellite in orbit
Right.
wasn't all that different from tracking the sun across the sky.
Makes sense.
It was a testament to their ability to think outside the box and adapt existing solutions to new problems.
That's a great example of how cross-disciplinary thinking can lead to innovative solutions.
It is.
They weren't afraid to borrow ideas from seemingly unrelated fields.
Nope.
So we've talked a lot about the local controllers and their sloppy algorithm.
Yeah.
Let's shift our focus back to the central station, the brain of the operation.
Right.
You mentioned that they initially planned to use a mini computer,
Yeah.
but their distributed approach allowed them to downsize to a much simpler system.
Right.
What What did the final design of the central station look like?
Well, remember how the sloppy algorithm drastically reduced the computational burden on the central station?
Yeah.
This meant they could ditch the expensive mini computer
Okay.
and opt for a much cheaper Z80 microcomputer instead.
That must have been a huge relief for their budget.
Yeah.
But I imagine programming a system this complex on a microcomputer was still quite a challenge.
It was, but they had a secret weapon, their software development method,
Okay.
which they called Cataract.
Cataract. That's an unusual name for a software development method.
It is, and it reflects their pragmatic approach. The
Mhm.
Cataract method was all about prioritizing basic functionality and delivering value quickly.
Okay.
They focused on getting a working system up and running as soon as possible, even if it wasn't fully automated or feature-rich.
So they were essentially adopting an iterative approach,
Exactly.
building and testing in stages.
They recognized that trying to perfect everything up front would have been too time-consuming and risky.
Right.
Instead, they focused on getting the core functionality working first,
Okay.
and then gradually adding more automation and sophistication
Right.
with each subsequent software build.
It sounds almost like a precursor to like modern agile software development.
You're absolutely right. It was a remarkably forward-thinking approach that allowed them to mitigate risks, adapt to changing circumstances, and ensure they could meet the tight installation deadlines dictated by the mechanical and thermal components of the power plant.
That's impressive. They clearly understood the importance of iterative development and delivering value incrementally. Speaking of delivery, I'm curious about the communication system they used to connect the central station to all those local controllers spread across the solar field.
Right.
What technology did they settle on?
They considered two main options.
Oh.
Ethernet, which was the new kid on the block, offering higher bandwidth,
Right.
but carrying more risk
Yeah.
because it was so new.
Yeah.
And then a more traditional twisted pair shielded cable system designed for lower data rates, but known for its reliability.
So a classic battle between the bleeding edge and the tried and true.
Right.
I'm guessing they went with the reliable option.
You know them too well. They opted for the tried and true twisted pair cables, and for good reason.
Right.
Their sloppy control algorithm and the relatively slow movement of the mirrors meant they didn't need the high bandwidth of Ethernet.
Right.
The twisted pair cables offered a robust, low-cost solution perfectly suited to their needs.
Plus, I bet troubleshooting would be a lot easier with the familiar twisted pair, right?
Absolutely. And they made it even simpler by choosing a polling communication protocol.
Okay.
So the central station would just query each LOC in turn using short ASCII commands and responses transmitted at a leisurely 1200 baud.
Wow.
Imagine a technician could literally hook up a handheld ASCII terminal to the network and monitor the traffic.
Talk about keeping it simple. It's amazing how they managed to create such a robust and reliable system using what we might consider, rudimentary technology today.
Yeah.
Now, let's dive into the heart of the system, the local controller or LOC,
Okay.
the little workhorse that made it all possible.
Yeah.
Each one was responsible for controlling a single mirror.
Yeah.
And they faced some unique challenges in their design. Right?
Yep, absolutely. Remember, these LOCs were operating in a harsh desert environment, exposed to extreme temperatures, dust, and the occasional curious critter.
Right.
They had to be tough, reliable, and designed for easy maintenance.
So they were like miniature fortresses protecting the brains of each mirror.
Yeah.
What were some of the key design considerations for these LOCs?
Well, they had to be, compact, fitting snugly onto the back of each mirror.
Right.
They had to be able to withstand the harsh desert elements.
Yeah.
And they had to be designed for easy troubleshooting and repair.
Yeah.
Because imagine trying to diagnose a faulty LOC in a field of hundreds of mirrors.
I'm already feeling a sense of awe for the engineers who design these little marvels. But I'm particularly intrigued by the position sensor they chose.
Okay.
You mentioned it was an unconventional option. What made it stand out?
This is where their thorough analysis and willingness to to challenge assumptions really shines through.
Okay.
They had three main contenders for the position sensor.
Okay.
A pulse counter, a potentiometer, and a digital optical sensor.
Right.
Each one had its own kind of set of pros and cons.
Okay, let's break those down.
Well,
what were the considerations for the pulse counter?
The pulse counter was a relatively low-risk option.
Okay.
It simply, counted the revolutions of the motor to determine the mirror's angle.
Yes.
Straightforward, right?
Yeah.
But it also required additional, mechanical and electronic components, adding complexity and potential points of failure.
Mm-hmm.
Plus, it would have been susceptible to errors if the motor slipped or missed steps.
So not the most elegant or reliable solution.
Right.
What about the potentiometer?
The potentiometer offered simplicity.
Oh,
its resistance would change with the mirror's angle,
Hmm.
providing a direct measurement.
Right.
But potentiometers, they're prone to wear and tear,
Yeah.
especially in a constantly moving system like this.
Yeah, okay.
They were concerned about their long-term reliability
Right.
and the potential for drift over time.
It makes sense. They wanted a system that could operate reliably for years
Right.
with, minimal maintenance.
Exactly.
So that leads the digital optical sensor.
Yeah.
What made it the winner?
They recognized that the optical sensor, while more expensive up front, it offered the best combination of accuracy, reliability, and long-term stability.
Mm-hmm.
It provided unambiguous position information in digital form,
Okay.
eliminating the need for complex signal processing or calibration.
It sounds like the clear choice for a system designed for simplicity and robustness.
It was.
But I'm picturing this optical sensor attached to the mirror,
Yeah.
and I'm struggling to visualize how they made it work, like mechanically.
This is where a bit of ingenuity comes in.
Okay.
One of their mechanical engineers,
Yeah.
a brilliant guy they called Rogo,
Okay.
came up with a clever solution.
Okay.
Imagine a pendulum-like weight
Okay.
hanging from the optical sensor shaft.
Okay.
As the mirror moved,
Yeah.
the angle of the pendulum would change, and the sensor would accurately capture that change.
That's such an elegant solution. It's like they harness the power of gravity
They did.
to create a simple and reliable position sensor.
Right.
And I love that it was a collaborative effort,
Yeah.
with a mechanical engineer playing a key role.
Yeah.
It highlights the importance of diverse perspectives in systems engineering.
Exactly. And they didn't stop there.
Yeah.
They enclosed the whole pendulum and sensor assembly
Yeah.
in a weatherproof housing, protecting it from the harsh desert environment and making it easy to attach to the mirror.
Smart move.
Yeah.
Sounds like they really thought through every detail.
They did it.
But didn't you mention they had some issues with the sun sensor,
Right.
despite it being a fairly standard component?
Yeah, the sun sensor saga.
What happened there?
It's a classic case of overlooking a seemingly insignificant detail
Okay.
that ended up having a major impact.
Mm-hmm.
The sun sensor used a lens to focus sunlight onto a pair of photodiodes,
Okay.
which generated a signal based on the intensity of the light.
Okay.
During assembly, these photodiodes were glued to a base plate.
Okay. Nothing unusual so far.
Yeah.
What was the problem?
Well, the physics department, the guys responsible for the sun sensors,
Yeah.
they didn't specify that the glue shouldn't cover the light-sensitive surface of the photodiodes. They figured, hey, the glue is transparent, what's the harm?
Oh, no, I can already see where this is going.
You guessed it. Over time, exposed to the intense desert heat,
Yeah.
the glue slowly became opaque, essentially blinding the sun sensors.
Oh, wow.
They ended up having to replace all of them,
Right.
a costly and time-consuming process.
That's a tough lesson learned.
It is.
It highlights how crucial it is to consider long-term effects and avoid unnecessary components or processes. What's that saying? If it doesn't make a difference, don't do it.
Exactly. And this keep it simple philosophy was evident in their approach to power distribution as well.
Okay.
Their initial plan was to use a 240-volt three-phase system.
Right.
But they encountered problems with the silicon-controlled rectifiers in the motor controllers.
Okay.
So instead of trying to fix those issues, they decided to simplify.
Okay, so what did they end up doing for power distribution? Did they switch to a completely different system?
They adopted a clever mix of 440-volt and 110-volt systems.
Okay.
So the 440 volts were used for the main power distribution
Right.
across the field, minimizing losses over long distances.
Okay.
And then they strategically placed power distribution units, or PDUs,
Yep.
that steps the voltage down to 110 volts for the LOCs and motors.
I see. So they used the higher voltage for efficient transmission,
Right.
and then stepped it down for safer and a more reliable operation at the individual mirror level.
Exactly.
But wasn't testing those 110-volt motors a challenge back in their lab in Jerusalem?
Yeah.
Didn't they have a different voltage standard there?
That's where their practical problem-solving mindset really shines.
Okay.
They simply used a standard 240 volt to 110 volt transformer to test the motors.
Okay.
No need for fancy equipment or custom solutions. They made it work with what they had.
It's another example of their resourcefulness and adaptability.
It is.
It seems like they were always looking for the simplest and most practical solution.
Absolutely. And those the step-down transformers and the PDUs, they also acted as transient suppressors,
That's right.
adding an extra layer of protection against electrical surges.
Talk about turning a potential problem into an advantage. They really had a knack for that.
They did.
But let's shift gears now and talk about how they put it all together. You know, the testing, manufacturing, and integration phases of this ambitious project.
This is where their hands-on practical approach really shines.
Yeah.
They were dealing with, components from all over the world, tight deadlines,
Right.
and the pressure of creating a system that had never been built before.
It sounds like a recipe for chaos.
Yeah.
How did they manage to keep everything on track?
Well, they had to get creative with their testing, since they didn't have the space to build a full array of hundreds of LOCs in their lab in Jerusalem.
Right.
So their solution, a LOC position emulator.
A LOC position emulator. What is that?
It was essentially a counter that simulated the mirror's movement, allowing them to test the central station software and the LOCs separately without needing a physical mirror.
So they created a virtual mirror to test the system in parts. That's some clever engineering.
Right.
What about the actual manufacturing process?
Yeah.
How do they ensure the quality and reliability of hundreds of identical LOCs?
Simplicity and quality were their guiding principles.
Okay.
They designed the LOCs for modular construction with units that snap together easily.
Okay.
Reducing the risk of assembly errors.
Okay.
They used pre-made cables with connectors, which streamline the installation process and minimize the chance of wiring mistakes.
It sounds like they were taking every step to prevent errors.
They were.
And ensure consistency.
Yeah.
Did they have any special quality control measures in place?
They did. And this one really stood out to me. Yeah. Each printed circuit board was signed by both the builder and the tester.
Wow. That's a real sense of ownership and accountability.
It is.
I bet it instilled a sense of pride in their work.
Absolutely. They fostered a culture of quality and craftsmanship, which clearly had a positive impact on the reliability of their product. And this focus on people extended to their decision-making process as well.
So how did they approach decision-making, especially given the lack of formal requirements documents?
They adopted a just-in-time philosophy, developing test procedures and integration plans as needed, adapting to evolving circumstances and making decisions based on the information available at the time.
It sounds almost like controlled chaos, but they clearly had a deep understanding of the system.
They did.
And the confidence to make decisions on the fly.
And it worked. They delivered a remarkably successful system on time and within budget, despite all the challenges they faced.
Yeah.
It's a testament to their ingenuity, their adaptability, and their unwavering focus on the essentials.
What an inspiring story. They truly embodied the spirit of innovation and problem solving.
They did.
But we've only scratched the surface of the lessons we can learn from LizSegs 1. There's so much more to unpack, from their keep it simple philosophy to their emphasis on people over processes.
Right.
Let's take a short break, and when we come back, we'll delve deeper into the key takeaways from this groundbreaking project, and explore how these timeless principles can be applied to our own projects and challenges. Welcome back. So we've been on this amazing journey exploring, all the intricate details of Liz Sedgy's ONE.
Yeah.
A pioneering project that really defied the odds and kind of ushered in a new era of solar energy.
It did.
But, beyond the technical marvels and the clever solutions,
right.
What truly stands out are those timeless principles.
Yeah.
That underpin their success. And these are lessons that go way beyond engineering.
They do.
And offer valuable insights for anyone tackling complex challenges today. So
absolutely.
Ready to extract some wisdom from this groundbreaking project.
Absolutely. What fascinates me is how a project completed over 40 years ago using technology that we might consider primitive today, still holds such valuable lessons in systems engineering. It's a testament to the enduring power of these fundamental principles, like simplicity, clarity, and a focus on people.
Let's start with their keep it simple philosophy, which seemed to kind of permeate every aspect of their approach. Was this like a conscious choice, or was it just a consequence of the constraints they faced?
It was probably a bit of both.
Okay.
They had limited resources, those tight deadlines, a multinational team, with communication barriers.
Right.
Simplicity, in a way, it became their survival strategy. But as the project evolved, it kind of transformed into a core design principle.
Okay.
They constantly ask themselves, what's the simplest way to achieve this functionality? And can we eliminate any unnecessary complexity?
Right.
And they weren't afraid to challenge conventional wisdom, even when it meant going against established engineering practices.
The decision to use a sloppy algorithm for mirror positioning is a perfect example.
Oh, it is.
It seems kind of counterintuitive.
Yeah.
But it turned out to be like a stroke of genius.
It did.
It reminds me of the saying, perfection is the enemy of good.
Right.
Sometimes striving for absolute precision can lead to unnecessary complexity and delays.
Exactly. They recognize that a simpler self-regulating system, while perhaps not as accurate in theory, could actually be more robust and reliable in practice.
Right.
And allowed them to use, less expensive hardware, simpler software, which were, crucial factors given their constraints.
Their emphasis on people over processes was also striking.
Yeah.
No formal requirements, documents, decisions made on the fly, a collaborative approach to problem solving.
Right.
It seems almost like counterintuitive to traditional engineering approaches, which often prioritize rigid procedures and documentation.
That's where their trust in their team's expertise really shines through. They had a highly skilled and experienced group of engineers who deeply understood the system and could make informed decisions without being, bogged down by bureaucracy.
Yeah.
They fostered a culture of open communication, collaboration, and empowerment, which, allowed them to adapt quickly to changing circumstances.
It makes me wonder if we sometimes overcomplicate things with our processes and documentation. They seem to thrive in a more agile and adaptable environment.
They did.
It's a powerful reminder that people are at the heart of any successful project.
Yeah.
And sometimes giving them the freedom to make decisions and solve problems can lead to the best outcomes.
Absolutely. And let's not forget their knack for asking the right questions.
Right.
Early on, they didn't have clearly defined requirements, but they had a crystal clear understanding of the system's purpose and the critical challenges they needed to overcome.
Right.
They constantly ask questions like, what are we ultimately trying to achieve? Yeah.
How can we measure success? What are the biggest risks and how can we mitigate them?
It seems like asking the right questions helped them, cut through the noise and focus on what truly mattered.
Right.
And they weren't afraid to look outside their own field for inspiration, like their adoption of a pattern matching technique inspired by satellite control systems.
They were masters at recognizing that someone somewhere had probably already solved a similar problem.
Right.
It's a valuable lesson for anyone tackling a complex challenge. Don't reinvent the wheel.
Yeah.
Look for existing solutions, learn from others' successes and failures, and adapt those lessons to your own context.
And that brings us to what I consider one of the most important takeaways from this deep dive. The concept of meta lessons.
Right.
They emphasize that not all lessons learned can be applied blindly to every project.
Yeah. We need to critically analyze the context, the specific circumstances, and the unique challenges of each situation.
Yeah.
What worked for LSX 1 might not work for every solar power plant,
right?
Let alone, every engineering project.
It's a crucial point.
Yeah.
We need to be thoughtful about how we apply lessons learned, always asking ourselves, why did this particular approach work in this specific case? And what's different about my project?
Yeah.
What are my unique constraints and opportunities?
It's about understanding the underlying principles, not just blindly copying the solutions.
Right.
So it's about extracting the essence of their success, the core principles that guided their decisions, and then adapting those principles to our own, unique challenges and context.
Right.
That's the real power of studying projects like LSX 1. It's not just about replicating their solutions. It's about learning to think like they did with ingenuity, with adaptability, and a relentless focus on the essentials.
Their story, it's a reminder that even with limited resources and seemingly impossible obstacles, human ingenuity and a commitment to simplicity, they can achieve remarkable results. It's a source of inspiration for anyone facing, complex challenges today, proving that innovation can thrive even in the most unexpected places.
As we wrap up this deep dive, we leave you with this final thought. What seemingly insignificant details in your current project might have a huge impact down the line?
That's a good question.
Remember the sun sensor glue.
Yeah.
Sometimes the smallest things can make the biggest difference.
They can.
So keep asking the right questions, embrace simplicity, and never underestimate the power of human collaboration.
Great advice.
Until next time, keep diving deep.
I hope you enjoyed today's deep dive. Why not take a moment and join the discussion in the LinkedIn group Tackling Complex Problems. Take care.